So today's my talk presentation title is Microstructure Characterization in Magnesium Dioxide and other Superconducting Materials. So let me start with the introduction of the purpose and method of microstructure observation of superconducting materials. So we will make a clear superconducting microstructure factor on polycrystalline superconducting materials. And then in the results and discussion part, I will show about the microstructure of the Lgbt wires fabricated the in situ method and the ex situ method. So in this presentation, so we focused these two kinds of method. And after that, I will summarize. So first of all, I will show about the microstructure factors in superconducting materials. So in large scale, it is important that the reproducibility and uniformity. And in macro scale and nano scale, so it is necessary to control grain structure, grain texture, defect, and atomic displacement. So to fabricate the high critical current superconducting materials, so it is necessary to control multi-scale structures. So we try to obtain the mechanism to control multi-scale structures for enhancement critical current by several microscopies. Okay, in this slide, let me briefly describe about the microstructure factor of Lgbt polycrystalline materials. So the advantage of Lgbt is easy to fabricate and high TC on metallic superconductors. But the critical current is insufficient for practical using because the packing factor is only 50 or 60% fabricated by in situ PIT method. So for consideration of the JC of Lgbt, we think the connectivity is the key parameter because the connectivity of the Lgbt has a positive correlation with the JC. And the connectivity is calculated by the packing factor and the grain boundary structures. So in other words, the packing factor and grain boundary are important microstructure factors of Lgbt. Okay, I move to the result part. So the first result about the in situ Lgbt. So here is the sample preparation. The method is an internal magnesium diffusion method. So this wire fabricated in Professor Kumakura's group, and the IMT wire has a high level critical current properties. And this critical current sensitive with heat treatment temperature. So in this part, we try to elucidate the relationship among the critical current, heat treatment temperature, and structure using by this kind of several electron microscopies. So this is I think image, the wire heated at 640 degrees, and this wire has the highest values of critical current. And so this direction is a drawing direction. It is corresponding to the electrical current direction. So it seems some of brightness area, so brighter area close to center of filament, and the dark area close to the metalysis, and the brightest areas in the here. From team result, Lgbt crystals distribute is only this brighter area that we call the crystalline area, and this outer area has magnesium oxide particles and amorphous borons, so it means a non-crystalline area. And this brightest area, so filled with the Mg to Si crystals. So it seems to distribute along with the drawing direction. And this Mg to Si is formed by reacting magnesium and silicon carbide particles. So it means that this secondary phase can be controlled by selecting the additive materials for carbon displacement. So the most advantage of IMD wires, this Lgbt crystalline area with forming the superconducting Lgbt crystalline area with high packing factor, and as shown in this image, the packing factor is almost 100%. So then I focused on this area. So from high magnification SN image, this Lgbt crystalline area has some of the dark regions. And from this diffraction pattern, so this dark region corresponds to the amorphous residual boron grains. So the wire's packing factor is 75%. Of course, this value is higher than any other MGBT wires fabricated in such method, and it is the reason that this wire has a high critical current. On the other hand, these residual boron grains decrease the packing factor and JC of this wire. So if we can control this residual boron, the wire has can be enhanced JC properties. So this figure shows the mechanism of remaining boron grain in superconducting area. So this figure from the Professor Hatta's group's papers, which is an elemental distribution of LGBT wires fabricated a PIT method at the 600 degree for 1 minute. So this area is an initial boron grains areas, and from this magnesium atom distribution, so magnesium atom infiltrates the boron grain from outside for forming the MgB2. So if the amount of the magnesium atoms is insufficient for forming MgB2, this center of area remaining as a residual boron grain. So it means the residual boron grain may be controlled by the length of the magnesium infiltration into boron grain by heat treatment, temperature, and time. So here image shows the IMD wire fabricated at 800 degrees for 1 hour. And the residual boron decreased 25% to 7%. But the wire of the critical current is almost zero. So because this crystalline area and the non-crystalline area is distributed uniformly, and this MgP2 crystalline area is not connected along the transport direction. So from this result, we suggest a microstructure evolution, and the control of distribution of magnesium infiltration is a key factor for fabricating high critical current properties MgBT wires in such method. So second result about the XH MgB2 bulks. So the advantage of XH MgB2 is that it is reached high packing factor and reduce of residual boron. So here shows the method of the XH MgB2 bulk preparation. So this bulk fabricated in Professor Yamamoto's group. So here shows dependence on sintering time and critical JC and connectivity. So connectivity increases with so increasing sintering time. So the packing factor is 78% and connectivity is 21% of bulk sintered at 900 degrees for 96 hours. In contrast, the packing factor is 75% and connectivity is 40% of MGB2 fabricated IMD method. So this low connectivity is the point of the microstructure issues of ex situ MGB2. So here shows them precursor powders of ex situ MGB2. So this precursor has many of aggregate, and this aggregate, so from this high magnification image, so this aggregates consist of polycrystalline MGB2. After sinters 24 hours, many of aggregates connect with each others, but then from this high magnification image, so this connection area and here, this area is too narrow, and we called this area the neck area. And this neck area includes some fine particles, and so in this particle is magnesium oxide. So even sintered 96 hours, and the neck parts are still remaining, as shown here and here. And some of the neck area has this bright region here. From diffraction pattern, this bright region corresponds to the magnesium oxide particles. So this result shows that these neck areas consist of few MGB2 grains and magnesium oxide particles. So this neck area caused low connectivity and low JC on ex situ MGB2. So for enhancements, so this neck area and connectivity, so proceeding grain growth is seems to be better solution. However, the no grain growth of MGB2 occurred during sintering at 900 degrees. So here shows the inverse pole figure map of 96 hours sintered bulk, and here shows the relationship between the grain size and the sintering time. So it seems the grain size of MGB2 is hardly change even sintering the 96 hours. So from the result, we suggest two methods for enhancement connectivity on ex situ bulk. So one is a pore size reduction before sintering by reducing the size of MGB2 grain aggregates. So it means that this large size of pores from the space at the precursor powders. So if we can make the fine precursor aggregate, this space is decreased. And the other is magnesium oxide removed from the surface on initial MGB2 powders before sintering. So it can reduce this kind of neck part. Okay, here's summarize. I show the microstructure characterization for enhancements critical current properties. So the key factor for the critical current is a difference on fabrication method of materials. So we need to use a multi-scale and multi-dimensional observation. So now our recent topics is here. So we try to start using the three-dimensional observation on superconducting polycrystalline bulks. That's all. Thank you for kind attention.
Thank you very much for this interesting talk. There's quite a bit of work done here, and I would like to know how do you remove magnesium oxide from the surface of the magnesium diboride?
Yeah. One method is one method is a ball milling and remove the surface area on the particle.
Okay, any other questions? Please.
Thank you. Very nice talk. I was wondering that whether the MgO is a very thin layer that is formed and it is at the intergranular area throughout the material. Is that a correct interpretation?
So you mean MgO area?
Yes. Is the MgO sort of like an impurity that accumulates in the intergranular area?
So you mean like here? So you mean this kind of area? This MgO area?
Well, I would expect that mainly you have Mgb2, and if you have MgO there, when you have a sintering process or any process with mass transport, then in some way, if there is a reaction that forms this MgO somewhere, I would expect it to be accumulated in interface areas, so that this would be in a polycrystalline material. It would be in the intergranular area, intergranular region, in granular junctions in some way. Or is that not what you see, what you observe?
So you mean the reasons? So you mean the reasons the MgO particle are forming? Sorry.
Or is it separate particles that form throughout?
Yeah, separate.
Yes.
Yeah.
Okay.
Yeah.
Okay.
So this MgO particle distribute on the surface. This surface aggregates maybe like the surface area. Like here, maybe this particle is MgO, and this MgO concentrates the neck area and forming the like kind of this area, I think.
Yes. Okay. Thank you very much.
Thank you.
Okay, are there any questions inside the room? No. Okay. You have online questions, I think. You may look at your chatting area.
Yeah. So, Professor Yamamoto, do you have a grain boundary team image? So this I don't have this kind of the neck areas structures, but I'm sorry, I don't prepare this presentation.
Okay.
Grain boundaries are clean or dirty with image. Sorry. So grain boundary is so here this grain boundary is clean. It's without the magnesium oxide particles on the atomic scale.